Hi, my name is Seyed from EDD Academy, and today I'm going to be covering exponential models using differential equations from Unit 7. First, what is an exponential model with a differential equation? A differential equation modeling an exponential situation follows the following formula. dy dt is equal to ky. Now, it always doesn't have to be with respect to time, but I just had to use some kind of variable here. K is a constant in this situation, so you could probably just tell from this that something like e to the power of kt would be a solution to this, because the derivative of e to the power of kt is just k times e to the kt, and that's just k times y. And the general solution to this is always y of t is equal to e to the power of kt plus c, the constant of integration. Or if you bring it out by writing it as e to the power of c times e to the power of kt and just condense that into one constant, c sub e times e to the power of kt. Alright, this is best demonstrated through an example. So find the particular solution for the following differential equation given that at time t is equal to 0, y of 0 is equal to 10. So dy dx is equal to 20 times y of t. We know that the solution to this equation is of the form y of t is equal to e to the power of kt plus c. We just need to find c since k is equal to 20. Plug in t is equal to 0 and y is equal to 0, y of 0, and solve. 10 is equal to e to the power of 20 times 0 plus c, which is equal to e to the c. Taking the natural log of both sides, we can see that clearly the natural log of 10 is equal to c. Plug that all in, and then we end up with y of t is equal to e to the 20t plus ln of 10 is equal to 10 times e to the 20t. Okay, now here's a really simple situation. The derivative of y of x is equal to 5 multiplied by the function. Write a differential equation representing the situation. So the answer, this is very straightforward. We'll just have to put the words into math form. So the derivative of y, dy dx, is equal to 5 multiplied by the function 5y. Very simple. This is just a quick throwback to the first lesson, modeling situations with differential equations. Solve that previous differential equation, dy dx is equal to 5y, under the initial condition that y of 0 is equal to 5. Alright, this is a good callback to some previous topics, namely separation of variables and initial conditions. So separation of variables, dy over y is equal to 5 times dx. Integrate this, and I'm not going to use the physics method this time, but it's a nice method if you want to use it. So the integral of dy over y is equal to the integral of 5 dx, which becomes the natural log of y is equal to 5x plus c, raising that to the natural power, and you get y is equal to e to the 5x plus c. Finally, apply the initial conditions. So that was the general solution. And now we just plug in y of 0 and 5 for y, and we get 5 is equal to e to the power of c. The natural log of both sides yields c is equal to the natural log of 5. So our final answer would be, by plugging all of that back in, y of x is equal to e to the 5x plus natural log of 5 is equal to 5 times e to the 5x. Now find the solution to the following differential equation given that y of 1 is equal to 6. We've seen this equation before. This was actually the first example, but this is under a different initial condition. So we could use separation of variables, or we can use a general solution like we did in the first problem and plug in the appropriate values. The second one is much easier, so we'll just use that one. So plug in k is equal to 20. Apply the initial condition. 6 is equal to e to the power of 20 times 1 plus c. Take the natural log and subtract 20. Okay, now plug it in, and we're done. Okay, so then our final answer is y is equal to e to the 20x plus natural log of 6 minus 20. So thanks for watching this short video from EDD Academy. There really wasn't much to cover in this one since it was really just a blend of topics from previous subunits, so sorry for the short length. So I hope to see you guys later. Bye.